If you had to pick a catastrophic event to remove all human life from the planet, I'm sure an eruption from a supervolcano would be near the top of the list. Well, there are some theories that suggest that this almost became a reality. Let's take a look. Today we're traveling to Indonesia, Lake Toba to be exact, in Sumatra. Lake Toba was the site of a supervolcanic eruption that occurred around 74,000 years ago. But what is a supervolcano? Toba is one of 20 supervolcanoes on Earth today, the most famous being Yellowstone in the USA. A supervolcano is one that, at some point in history, released more than 1,000 cubic kilometers of magma during an eruption, and Toba certainly qualifies. The volcano threw an estimated 2,800 cubic kilometers of volcanic ash into the atmosphere, almost 3 times the threshold to make it a supervolcano. It is now a lake, due to the fact that it injected a vast proportion of its mass into the air during its catastrophic eruption. The eruption was 100 times larger than that of any other known in history, and is the largest in 28 million years. The eruption had an estimated volcanic explosivity index of 8, which is as high as the scale goes, giving it a description of apocalyptic. This left Lake Toba standing 100 kilometers long, 30 kilometers wide, and 505 meters deep, or 62 by 18 miles. And it was thought that this eruption had disastrous effects on the planet and its life, including humans. Apocalyptic indeed. Early research described how the catastrophic amount of ash and sulfur dioxide that was released into the atmosphere changed the climate across the globe. These gases and particles blocked sunlight from reaching the Earth, blanketing the planet and causing temperatures to drop. Scientists call this a volcanic winter, and it's exactly as bleak as it sounds, with a worldwide decline in temperatures between 3–5 degrees Celsius and up to 15 degrees C in higher latitudes. This might not sound like a lot, but it can have immense impacts on ecosystems when these changes happen quickly. Genetic evidence showed that this was a big enough shift to wipe out most early humans. Around 3,000 to 10,000 humans were estimated to be left alive, with the lowest estimates suggesting only 1,000 breeding pairs. Most of the surviving humans were in Africa, as it seems our ancestors in Europe and Asia didn't make it. This severe eradication of populations created a much smaller variety of humans to breed from, called a genetic bottleneck, which affected the genetic inheritance of all humans today. Compared with other animal species, there is a surprising lack of genetic diversity among humans. In fact, there is less genetic diversity between all 8 billion of us than there is in a closely related troop of 50 chimpanzees. The Toba catastrophe theory aimed to explain this lack of genetic diversity, that this supervolcano caused a mass global extinction of humans, almost resulting in our extinction. At least that's the theory. Modern research has cast doubt on the idea that early humans suffered dramatically from this volcanic winter. While genetic evidence does suggest a severe drop in human numbers around this time, other reasons, including migration out of Africa, seem to be far more responsible. Recent climate modeling studies suggest that this volcanic winter, while certainly disastrous, was more regionally localized instead of a global event. Impacts were harsher in the northern hemisphere than in the south, and it didn't seem to affect hominid species in Africa as much as once thought, with more survivors than just the 2,000 predicted earlier. Climate models predicted that the northern hemisphere experienced cooling of up to 10 degrees, whereas those in Africa barely saw 4-degree changes, even at the harshest eruption parameters. Africa and India may have seen reduced precipitation after the eruption, though. The theory goes on to hint at a group of early humans in Ethiopia known as Shinfa Matima 1, adapting to the drier conditions by shifting diets. Using the droughts to fish in shallow waterholes, they ate a more pescatarian diet as the Shinfa River dried out, adapting to survive. However, a lot of this genetic work was done in the late 20th century and was nowhere near as accurate as today's standards. This is where the arguments come in. Please like this video if you're enjoying it so far, and consider subscribing to support the channel and keep up to date with our adventures. We'd love for you to join us. Back to the latest evidence. A team in Oxford thought that if the eruption was so large, it should be noticeable in Lake Malawi, 7,000 kilometers west of Toba. It is located in the East African Rift Valley where our Homo sapien ancestors emerged some 100,000 years ago. The sediments in Lake Malawi are used as reliable records of climate change, analyzing organic matter found in its mud. Sediment cores were assessed, and the team did find some tiny glass shards the size of a human hair, about 30 meters deep in the mud. These were fragments of magma frozen in flight as they traveled from Toba. So the eruption certainly did reach Africa, although no other evidence suggests a dramatic change in climate. The populations would have seen ash falling from the sky, but they would not have suffered severe drops in temperature, as once thought. Lake Malawi analysis suggests the droughts previously mentioned more likely occurred 100,000 years ago and were not correlated to the Toba eruption. The bottlenecks around this time, and those around 50 to 60,000 years ago, are both now attributed to migrations out of Africa. After this time, populations exploded as we began advancing in technologies and languages, so all was not lost after the Toba eruption. But if there was a significant bottleneck, and it wasn't all caused by the Toba eruption, what actually happened 74,000 years ago? Evidence did point to severe climate fluctuations, and these likely confined many human populations to a few small refugees in Africa. One of these refugees, likely in East Africa on the Horn, became the launchpad for the small group of modern humans who left Africa. This founding population may have been as small as a few thousand individuals, which is what attributed the bottleneck to such small numbers. It wasn't that all the others got killed off rapidly, but that this main founding group was a small number. When they left, they carried only a fraction of the genetic diversity present in Africa. This is why humans outside Africa today have significantly less genetic variation compared to those who remained. This reduction in diversity had profound consequences, influencing how populations adapted to new environments and their susceptibility to diseases. Those groups left behind battled with droughts, predation, and increased competition for dwindling resources. The harsh Sahara Desert and Sinai Peninsula acted as barriers to movement for much of prehistory. Only during favorable climatic periods could populations cross into the Levant and beyond. If these subpopulations didn't move with the main group of our story, they missed their chance and eventually became extinct. The successful migrants took two primary routes out of Africa. The first was the northern route, crossing the Sinai Peninsula into the Levant. The second, and more significant, was the southern route, across the Bab el-Mandeb Strait into the Arabian Peninsula. Once in Arabia, humans followed the coastline, using the rich marine resources of the Indian Ocean as they spread into South Asia and beyond. The pace of this migration was remarkable. By 50,000 years ago, humans had reached India. By 45,000 years ago, they were in Southeast Asia and Australia. Europe and Central Asia followed around 40,000 years ago, and much later, around 15,000 years ago, humans entered the Americas via the Bering Land Bridge. So we have to be very thankful to these early ancestors for making such journeys. As humans expanded, they weren't alone. Eurasia was already home to other hominins, and these encounters profoundly shaped our species. First, there were the Neanderthals in Europe and Western Asia. We didn't just compete with them, we interbred. Today, about 1 to 2% of the DNA in non-African populations comes from Neanderthals. This interbreeding likely provided genetic advantages, such as immunity to local diseases. In Asia, humans encountered the mysterious Denisovans, another hominin group. Denisovan DNA is found in modern populations of Southeast Asia, Oceania, and East Asia. For example, up to 5% of the DNA of Melanesians and indigenous Australians comes from Denisovans, including genes that help them adapt to high altitudes. But the arrival of modern humans often spelled the end for these other hominins. Competition for resources, possibly combined with disease and climatic shifts, drove Neanderthals and Denisovans to extinction within tens of thousands of years after Homo sapiens arrived. Other hominins, like the diminutive Homo floresiensis in Indonesia and Homo luzonensis in the Philippines, also disappeared around this time. Whether through competition or ecological pressures, Homo sapiens emerged as the sole surviving hominin species. So while humans did experience a genetic bottleneck out of Africa as a result of harsh climates and rapid migrations, and also caused the extinction of their old neighbors, they intermingled with other hominin species to recover a portion of diversity from newer species. All of this shaped the way us humans function today, and not much of it was impacted by the Toba eruption as we once thought. Thanks for watching. Please consider liking and subscribing if you've enjoyed, and we'll see you next time.